Dr. Ward from the University of Texas at Austin, and she's going to talk about sparse recovery with minimal incoherence.
Thanks. I just want to start first by saying I'm also an academic child of Ingrid. And Ingrid, are you here? No? Okay, I'll do this at the end then. Okay. I know that this title is a little different from the one I had in the program, so I lied to you a little bit for dramatic effect. The title I had was Sparse Recovery Without Incoherence, and I'm sorry, that was a bit dramatic to get people to come. What it more appropriately titled Minimal Incoherence. So let's start with just an example. This talk will be in the setting of compressed sensing. So I've put things on the grid for simplicity at the beginning of the talk. And the first application in compressed sensing I'm interested in is image processing, where we want to approximate an image from subsampled measurements in the 2D Fourier domain. Okay, so this was maybe one of the original motivations of compressed sensing. So I'm plotting the 2D Fourier domain, or K-space, on the left side of each figure. So the middle of that is low frequencies, and then as you go out away from the middle, the frequencies become higher on either of the two tensor products. This is in 2D. And so here are four subsampling strategies. So first, I just sample the very lowest frequencies. So this is low-pass filtering or deterministic sampling, and get a pretty good reconstruction. And then I sample from various power laws, which are more or less and less concentrated. And once the power law becomes sufficiently not concentrated around the center of K-space, reconstruction becomes very bad. If we zoom in on the fine details of the image, we see that actually deterministic sampling might look good globally, but locally it's not as good as recovering the fine local changes in the image as the power law sampling. So I know that it's a opening can of worms to say what's an optimal sampling strategy for imaging. Okay, I understand, but we have to put some model. So the model I'm going to consider is that images are sparse or compressible in wavelets or finite discrete differences. And I'm going to ask about an optimal sampling strategy in the frequency domain given this model, or one that we can actually prove something about. So the general setting for incoherent sampling, just n-dimensional signal with sparsity with respect to an orthonormal basis psi. I'm allowed to take an m by n measurement matrix, so long and fat, compressed measurements as substantive rows from an alternative orthonormal basis phi. So this is the constraint. And I want to derive sampling strategies to recover X from these compressed sensing measurements. So, I mean, it's essentially folklore now. We all know that we can get sort of the best or really good sparse recovery results if our sampling dictionary is mutually incoherent with the sparsity basis, where by mutual incoherence, I mean that each of the elements of the orthonormal basis that we sample with is sort of maximally uncorrelated with the basis where we have sparsity. So all of these inner products are uniformly very small. So the classic example would be the discrete Fourier matrix and the identity matrix, okay, because the discrete Fourier matrix is uniformly bounded. So we know that for trying to recover signals with sparsity in the canonical domain, randomly subsampling frequencies is a strategy that we can get recovery guarantees for. So that's what the incoherent sampling is. So this is just a summary of what some of the results. So the result for incoherent systems is if the sampling basis and the sparsity basis are incoherent, like Fourier and identity, then a sampling strategy for which you can get guarantees is to just uniformly subsample M rows from our sensing basis. Pick M at random and reconstruct using L1 minimization. As Ben mentioned earlier, this is the atomic norm for sparse signals, and so I'm going to focus on sampling rather than reconstruction, but a typical or a result that's now well known in compressed sensing for this incoherent sampling setup is that if we take a number of measurements, M, so subsample a number of rows from this basis, and the number of rows is at least S, the sparsity level, and a few logarithmic factors in N, and also greater than or equal to kappa squared, where kappa is this constant on the incoherent factor between the two bases. Then we can get exact recovery for exactly sparse signals in the sparsity basis, and we also have stability. We can get instance optimal or achieve the minimax, almost the minimax optimal rate for arbitrary signals. And there's also robustness to noise, but just for simplicity, I'm not going to talk about that. Okay. But in important applications, the sensing and sparsity bases are not incoherent. Is there so what do we do here? Can I give you a strategy that says, well, this is at least the best you can do, or something close to the best you can do, given the sensing and the sparsity bases that you have? And again, back to the original example, a very important example where we don't have incoherence is when we are taking measuring images with frequency measurements. So again, my model for images is that they're compressible in wavelets. So if we look at this is just the 1D Haar wavelet basis and the 1D discrete Fourier basis. So if we're taking Fourier measurements of an image, we see that the very first element of the Fourier basis is the same as the first element of the wavelet basis. They're both constant. So what that means is that their mutual coherence is as bad as possible. It's equal to 1, meaning an atom from one and an atom from the other have maximal correlation. So, so any sort of sensing recovery guarantees we can't get with the sort of incoherent sampling results. Now, if we take a closer look at the coherent structure, because you say, well, yeah, the first guys are coherent, but then very quickly, when the wavelets become more localized, we have incoherence. So they're sort of incoherent. So if we take a closer look, we can calculate individually for each particular element of the Fourier basis the maximal inner product between that particular element of the Fourier matrix and all of the elements of the wavelet basis. And if we do that, we can calculate that, say in 1D, the coherence decays like 1 over the square root of the frequency, okay, as we go through individually the different frequencies. Okay, so this gives us a rate of decay of the coherence. Asymptotically, it's incoherent. And we can also do a calculation in 2D. We can calculate, again, that the coherences decay like 1 over the distance of the frequency from the origin in 2D K-space. Okay, so this motivated us to define the local coherences from a basis onto a basis. So instead of looking at the mutual coherence between my sensing and sparsity basis, I look at N, a finer measure. So I take the coherence between each of my N elements of the sensing basis and calculate its maximal coherence with the sparsity basis. And I call that vector of coherences local coherences. And proposed sampling strategy is to sample according to these coherences. Select M rows from the sensing basis, again some randomness, but now IID from a variable density where I choose a row proportional to, the square of this, the square of the factor kappa L. So the square of the local coherence. So the elements that are more coherent, I'm more likely to sample. Okay, again, reconstruct with, say, L1 minimization. So then we can show that, in fact, all of the results from compressed sensing that depend on bounded mutual coherence can be extended without any loss of generality almost to the setting where we have bounded average coherence, bounded average local coherence. So now what was the sort of L infinity norm has now become an average. And that's what the number of measurements should depend on, as long as you sample according to this variable density strategy. So in the particular case of Fourier and images, we find that the mutual coherence, it's very bad. So we would get an extra factor of n using the standard compressed sensing results. But we can calculate that the average local coherence is only log n because of our variable density decay. So if we sample frequencies from, in the 2D case, when we sample frequencies from the 2D Fourier space proportional to 1 over the squared distance from the origin, so that's our variable density strategy, then we can get these optimal minimax rates in compressed sensing up to this log factor. I'm actually going to come to this slide after I show you a picture, because I feel like a picture it's time for one. So just going back to the wet paint picture, so in blue, this is the power law density for which our theory applies. So theory and experiment agree somewhat. Clearly, if I were to sample from a density not as concentrated, it does worse. But actually, we find that when we look at sampling densities that are a little more concentrated, power laws that are more concentrated than what the theory says, we usually get a little better reconstruction. So that's something that we still don't understand, possibly because we're not taking into account the sparsity structure of images at all, just the coherence between the two dictionaries. And the proof of this result is actually very easy. It's essentially take the theory of bounded orthonormal systems, which is a continuous version of the mutual coherence results from compressed sensing, and do a change of measure, essentially, to derive a restricted isometry property, not for the sampling matrix, but for a preconditioned version of the sampling matrix. So by resampling and preconditioning, we can get a matrix with the restricted isometry property as long as we have bounded average local coherence. And for images, a better reconstruction strategy that does better than minimizing the wavelet coefficients in L1 is to do total variation minimization. And so we can extend also when reconstructing with total variation minimization these sort of minimax guarantees. And the proof uses a nice Bernstein type estimate from Ron DeVore and collaborators, which bounds the compressibility of the 2D wavelet coefficients by the total variation. So it's a little more technical than the other. There's been a lot of related work. Again, with this result for the MRI, I'm not saying that if you're actually going to do an MRI that you should sample according to this strategy, but I wanted to lay down some sort of results for some models for images. And so variable density sampling strategies in MRI have been used in MRI machines. If you know the radial line sampling that some machines do, the radial lines have average density of 1 over the distance squared to the origin, which is the density that we got. And then people had done some theoretical work, but without explicitly calculating coherences or getting stability or robustness results. So I'm going to make this talk sort of short, so I'm just powering through here. I just want to mention that this coherence-based sampling is a strategy that we can use far beyond the context of image processing or frequency and image processing. So there's a continuous version of the theory. By continuous, I mean my orthonormal basis is orthonormal with respect to a continuous measure instead of discrete, as we were talking about before. And one can consider orthonormal bases like the Legendre polynomials, which are orthonormal with respect to the uniform measure on their domain, but they're not uniformly bounded. They grow, they explode as the elements approach the endpoints, as you can see. And the interest is that smooth functions have decay with respect to their Fourier or Legendre polynomial expansions. So smoothness is a sort of structured sparsity. And so we might be interested in recovering functions with sparse expansions in Legendre polynomials. And if we calculate the coherence, we find in this case that the Legendre polynomials are not uniformly bounded, but we can bound their growth uniformly. They lie uniformly within a square integrable envelope function. And this is exactly the continuous analog of the average coherence. And so using that and driving the sampling strategy, we get out that the best sampling strategy within this framework is to sample points randomly according to the Chebyshev distribution, so more densely around the endpoints. And this is known, this agrees with classical results on polynomial interpolation and quadrature. It's known that Chebyshev sampling more densely around the endpoints is better for polynomial interpolation. But I just want to mention that we can also extend this to, say, spherical harmonic systems. And for spherical harmonics, the sampling measure, the coherence-based sampling strategy we get isn't classical. It seems to be a measure that I haven't seen before. So there are also some new things that comes out of this. Just illustrating why Chebyshev sampling is better for polynomial interpolation than uniform. And we can also extend these results to other settings like matrix completion. So here this is a little different. And in fact, I found that in the setting of matrix completion, where we have a matrix that's low rank, but I have no assumptions about the incoherence. My only assumption is that I have a low rank matrix. We found that coherence-based sampling in this setting turns out to be of the form sample entries from the matrix proportional to the statistical leverage scores of the matrix, or the projections of just the standard basis vectors onto the left and right subspaces. Okay, so the leverage scores have been known in statistics and in numerical linear algebra that this is a good sampling strategy for, say, if you're going to approximate a matrix by column subset selection or row subset selection, that this is exactly what they would do, except now we're just sampling entries instead of columns or rows. And so we can prove some exact recovery results for an arbitrary low rank matrix as long as the entries of the matrix, we choose them, or they're revealed to us proportionally to this coherence, this weighted sampling rather than uniform sampling. The motivation for this is that in certain applications, it's actually natural that you would more likely see the larger entries of the matrix, which is, roughly speaking, what the sampling strategy is. Say in global positioning problems where you see local distances between objects and not the faraway distances. So that means you're more likely to have the entries of the matrix where the dynamic range is larger, which is what coherence, what this is. And so this might explain why nuclear norm minimization or other algorithms might work for matrix completion in that setting. So to summarize, the take-home message is that in many sparse recovery problems, if you can get a bound on the coherence structure between your sensing basis and your sparsity basis, then you only need to have bounded average coherence rather than bounded maximal coherence to achieve the minimax optimal compressed sensing rates, as long as you sample proportional to the coherences. This is essentially just important sampling in compressed sensing. I decided that's all it is. There are many open questions. Structured sparsity, measurement error. There are still some questions related to the model for the error. Improved bounds for the coherent matrix completion are bound on the number of measurements is not tight, so that's an open problem. A really interesting direction, I think, is adaptive sampling in the setting of matrix completion. And this is motivated by a recent paper of R.D. Singh and her student, where they actually do matrix completion by adaptive sampling when they only require incoherence on one or the other singular subspace of the matrix, and not both. So can you somehow start by sampling the matrix uniform or without any prior knowledge, and then learn the coherence, learn the leverage scores of the matrix, say, or the optimal sampling strategy? That's all. Thanks. Oh, yes, Ingrid. Hi. I just wanted to say that, well, you're a great advisor, and thanks for being an inspiration. Happy birthday.
Any questions for Rick?
It's much more dense around the poles, and then a little bit more dense around the equator also. So it's this funky arc tangent type measure.
So it's not what you would expect by sort of the Legendre into one coordinate.
Right,
So
right.
there's also
It's not what you might expect. Yeah, and I haven't seen that measure anywhere.
One question about, so essentially you removed, in the matrix completion part, you removed the assumption that the U and B's are sort of uniformly
Yeah.
spread in the matrix, so
Yeah.
they're arbitrary,
Yeah.
but then they affect the sampling of the distribution.
Yes.
So,
Yes.
but then you get the higher exponent in N.
Well,
And so
it's not necessary. It's that's my conjecture. My conjecture is just we don't know how to get just the linear exponent.
But you think you could?
Yes,
Without
yes,
that?
definitely.
Oh, I see.
Definitely. Yes, yes. It's not sharp, I know.
Oh, okay.
Yeah.
It's not the case that maybe the localization of the eigenvectors regulates that N versus N to the 3/2.
No,
Oh.
I just don't know how to do the analysis.
All right, let's thank Rachel.